All right, time for week 4 theory video. So today we'll be dealing with semiconductors, transistors, and op-amps, operational amplifiers. So these are all based on semiconductors. It's actually what diodes are based off of as well. So semiconductors are kind of in the middle between conductors and insulators. So based on their conductivity, which is 1 over the resistivity. So we saw resistivity before. Conductivity is the inverse of that, so 1 over that. So conductors have really high values of conductivity. Insulators really low values, so 10 to the negative 12, negative 9. Semiconductors are kind of around the 1 range, so they're kind of right in the middle. 1 to 10 to the negative 3, so those are our semiconductors, usually made out of silicon or germanium. We use these in what's called a dope form, so we actually combine them with other elements, and that actually helps change the conductive properties. 2 ways to do this is the p-type and the n-type, just for positive charge carrying or negative charge carrier types. So the way we do this, you have a silicon atom. Silicon have 4 valence electrons, and so it's all bound up in covalent bonds, and this is kind of how it looks in general for silicon. You have these kind of wafers where the bounded with 4 other silicon atoms, kind of sharing those 4 valence electrons. So what we do to change that, 2 different ways, one for the n-type and one for the p-type. For the n-type, add a small fraction of phosphorus, so there's a few little phosphorus atoms in there as well. Phosphorus actually has 5 valence electrons, and so for the same crystal structure, you end up with an additional electron floating around. So there's additional negative charges when this is done. So there's these additional electrons that can basically move throughout the crystal, jump to different parts, and those are your negative charge carriers. That's why this is n-type. These electrons can jump to other places, and that's going to increase conductivity because we have these electrons moving, and electrons moving is essentially conduction. For the p-type silicon, kind of the opposite, we add boron, which has 3 valence electrons. So when it only has 3 valence electrons, only 3 pairs are able to be made. The 4th pair doesn't actually get made. There's what's called a hole. So a hole is basically just not an electron. But it's going to help us when we talk about current flow, because current is the flow of electrons, as we all know, but those are negative charge carrying atoms. Current we generally talk about as being positive when positive charges flow, and even though positive charges don't flow, we still kind of call that positive current. Same kind of thing happens here. We're going to talk about these holes actually flowing in some direction, but what's really happening is the electrons are going in the opposite direction. So I have some electrons that can jump from other atoms in this lattice and jump in to fill that hole. But when they jump in to fill that hole, they leave a hole somewhere else. So even though that hole is just being filled by an electron, that's what's really happening. We kind of see this hole show up over on the other side. And so that's kind of, we think of that hole as moving. And so that's kind of creating our current through the circuit. So that's kind of what I said before. The holes don't actually flow, but we still talk about them moving and the holes being the positive charge carrying devices. Some applications of semiconductors, we've already seen diodes. So diodes are essentially a combination of a p-type and an n-type semiconductor placed back to back. And that's what makes them work the way they do. We'll talk about that a little more in a few minutes. Some bipolar transistors. These are the types we're going to be talking about a little later. So generally, instead of diodes have 2, 1 p and 1 n type semiconductor. Bipolar transistors have 3, so either an NPN or a PNP. And we'll get to that in a minute. There's field effect transistors, which have kind of a different layout. And then other transistors as well that you may see. So as I mentioned, for diodes, you have a p-type semiconductor matched up with an n-type semiconductor kind of placed back to back. And so what happens if I add a voltage source to this, this voltage source is going to, essentially the positive side is going to attract the electrons. Now the electrons are already somewhat attracted to the holes because they want to fill their valence shells, but there's kind of a depletion region is what's called between these two. So there's kind of a voltage that needs to be overcome before these jumps can happen. So if I apply that appropriate voltage, there's enough attraction here for these electrons from the N-type charge carrier to jump over and fill these holes in the P-type charge carrier, and that's going to cause a flow of electrons. And as we all know, flow of electrons means current. So I get current in the circuit, again, as long as this battery is higher than the turn-on voltage, usually about 6 volts, as we saw last class or last week. If this battery is larger than that, I get a turn-on voltage and current flows. If I turn that diode around, so the P-type is on the left, N-type's on the right, same as before, but now I've changed the battery. So battery before, positive is on the left, negative on the right. Now this positive voltage is attracting the electrons to the right. So because they're attracted to the right, none of them want to jump across this depletion region. Similarly, these electrons on this side are going to fill holes on the right-hand side, but they're not going to have enough to jump across this depletion region. So that's my diode in the off configuration backwards. So that's why no current flows when these things are placed in backwards. So those are diodes, again, 2, 1P and 1N semiconductor. Transistors generally have 3, so either NPN or PNP. Transistors, these are bipolar junction transistors to be specific, and that's what we're going to focus on this week. Transistors are used for 2 principal uses. Either be a switch, so kind of like a diode to be on or off. These things also are going to take some effort to turn on or off. So you can use them as switches just by controlling the voltage into them. We're also going to see that they amplify current. So depending on how this is hooked up, I can have some current going in and then some current coming out, which is a lot higher. So these have 3 legs or 3 attachments. Just like the diode has 2 attachments, 1 to the N and 1 to the P. These have 3, 1 to the N, 1 to the P in the middle, and then 1 on the N on the outside, or alternatively, 1 on the P, 1 on the N on the inside, and 1 on the other P. So these are called the base, the emitter, and the collector. So collector and emitter on the outside, base is in the middle. This is the first transistor, way back in 1947. So it looked like these are the guys responsible for it. So we're going to look specifically at NPN transistors. PNP is very similar, just kind of opposite. So in either event, I'm going to need some positive voltage between the base and the emitter to make the holes and the electrons come close enough together that they can jump over, well, specifically that the electrons can jump over that depletion region. So if the transistor's off, I have this fairly big depletion region. It's too big for any of these electrons on the right to jump into those holes, so nothing is really happening. And so to get current to flow from the emitter to the collector, I'm going to need to make that depletion region more attractive. So to do that, I need some sort of voltage difference between the emitter and the base. So by doing that, applying some voltage, some positive voltage between those two, just like happens with the diode, that then makes these electrons want to jump over the depletion region and fill the holes. And when they do that, the majority of them keep going straight through because on the other side, it's a very thin depletion region. So most of them just carry straight on through and go to the collector. Some of them do go down to the base, but not as many because, again, this is a very small depletion region, so they generally just go straight through from the emitter to the collector in the on configuration. So again, PNP very similar to NPN, but kind of opposite. So NPN is normally off, like we just saw, but if I have a base voltage bigger than an emitter voltage and bigger than by about 0.6 volts, so the same turn-on voltage, I need that V base to be roughly that much bigger than my V emitter. That's going to make current flow between the collector and the emitter. PNP, again, the same but opposite, still normally off. This time I need the opposite, so kind of negative voltage on that one. V base to be less than V emitter by, again, about the same amount for current to flow between the collector and the emitter. So this leads to two important rules. NPN transistors, VC has to be greater than VE by at least a few tenths of a volt, again, roughly 0.6. So that's the first condition. Opposite for PNP, just set it greater than or less than. Again, this voltage drop is approximately 0.6 volts. Again, opposite direction for PNP. And that's, again, my turn-on voltage, like we saw for diodes. So another application of these transistors is as a current amplifier. So we look at the current into the collector compared to the current into the base. That ratio is called the current gain. So IC over IB is beta, my current gain. Typically, this is in the neighborhood of 100 or hundreds. And then using Kirchhoff's current, so I have IC coming in, I have IB coming in, so IE has to be the sum of the two. So IE is IC plus IB. You can relate that back to just IB because IC is IB times beta. So I can get my emitter current based on the base current given the current gain beta. And that's pretty much all we're going to need to know to analyze these circuits. So NPN circuit, I have some current IB coming in the base, have some current IC coming in the collector. Generally that's beta times IB, so usually a lot higher. And then same thing, my emitter coming out, I have total voltage coming in, it's beta plus 1. Beta plus 1, if beta is really big, is roughly the same as beta. So generally you have that IE and IC roughly the same thing. Same thing happens for PNP transistors, but again, slightly different. Again, I also need this voltage to be about 0.6 volts bigger. But again, here I have some base current this time coming out, some emitter current this time going in, some collector current going out, and again, collector and emitter currents are roughly the same thing, as long as beta is big, which it usually is. A whole bunch of different types of transistors do various things. We generally use ones that look like this. So the ones you'll be using in the lab look like these guys up here, have a little flat side and kind of semicircular, 3 legs coming out, emitter, collector, and base. So speaking of that, it's very important to know which one's which. So which one's the emitter, which one's the collector, and which one's the base. As I said, the base is always the one in the middle. So for NPN, it's one connected to the P-type semiconductor. So therefore, B is usually the middle one. And then emitter and collector depend on what side you're on. Usually, this is the orientation, so there's a flat side up, emitter is usually on the left, collector is usually on the right. But again, make sure that's the same one you have. Now I'm going to take a more detailed look at these transistors as voltage amplifiers. So I have some voltage in coming into the base. I'm assuming this voltage in is bigger than the turn-on voltage of my transistor. So I'm assuming that V in bigger than voltage between the base and the emitter to turn it on. Again, usually 6 volts, 0.6 volts there. If that's the case, then I can find my current. So current is V in minus VB on. Again, that's how much I need to turn it on. So that's basically the voltage coming in to the base. Divide that by this resistance RB, and that gives me the current. And then I can find my collector current using the current gain beta. So IC is beta times IB. So beta times the relationship we had up there. And then based on that current IC, I can get V out. So V out is my source voltage minus the voltage drop across RL, which is RL times IC. And then IC is this expression up here. So essentially I have my voltage source up there minus beta relationship between resistors RL over RB, and VB minus VB on. So V out is a scale version of V in, so there's a scaling factor, beta times the resistances compared to the voltage going in. So if I look at the change in voltage, so how does V out change if V in changes? So just change V out to V out plus delta V out, change V in to delta V in, and then kind of group terms together, and grouping terms together, one of them just becomes V out, and then I'm left with essentially this beta RL over RB times delta V in. So again, there's my voltage scaling factor, generally called AV, so that's delta V out over delta V in. So AV is my voltage amplification factor. It's also called the gain. So a lot of times this is just the gain. If you're asked for the gain of that transistor, that's what this is. That's what you're asking for. And again, it's just beta times RL over RB. There's a minus sign involved. So minus sign means my output is going to be 180 degrees out of phase with the input, or negative depending on whether I have some sort of alternating current or direct current going in. And that, of course, is assuming that my current is within the cutoff region and the saturation region. So cutoff region, I need to have enough voltage to get it going. So then when it's going, I get this amplification factor. Saturation region is kind of like too much current, too much voltage. It is too much, so the transistor or diode generally going to fail. You can see there's a few elements here. There's this VB on, which is 0.6 volts. There's some sort of V in as an AC source. There's a VS coming in to power it. Again, that's some sort of DC level. And then my V out is, again, this V in, but shifted 180 degrees and amplified. So bigger amplitude, shifted 180 degrees. If I want to have a purely alternating voltage, so a lot of radio and audio applications want just a pure AC source. They don't want any DC offset. Generally what you do is you take these amplifier stages and isolate them from each other. That's going to block any DC components, add some capacitors in there as well. So these are capacitor coupled and transformer coupled stages to, again, block out that DC component. And here we don't have any base resistor. So the previous one we had a base resistor to provide some impedance. In this case, we don't need to provide the impedance because capacitors can provide impedance as well. So they're providing essentially not only blocking that DC component, but also doing the job of the resistor to provide impedance as well. So now we get to operational amplifiers, or op amps. These are another very basic building block. They're used a lot, so we'll be using them a lot as well. They're generally some combination of a whole bunch of transistors, resistors, capacitors, and other components to create an amplifier. So kind of like the amplification you saw for the transistors right now. These act as amplifiers as well. They generally have 5 pins or 5 inputs or outputs. Actually, generally 8, but 3 of them aren't necessarily always used. So you have a supply voltage, a positive supply, and a negative supply. So these things need power for them to work. So you need to supply some positive voltage source. And then you have two leads in non-inverting input V plus and inverting input V minus. So obviously the positive one is going to give you the positive voltage coming out. Inverting one is going to give you a negative one or shifted by 180 degrees on the output. So you have some voltage coming in and then some voltage coming out, and that voltage coming out is generally amplified. These are usually given on an IC chip, so a little rectangular chip with 8 different leads. We'll see a picture of that in a minute. And then you have different leads, so which pins connect to what in terms of coming in, coming out. So we have output pin, input pins, and my voltage to power the op amp, positive and negative as well. So generally, your power is going to be applied at your VS and plus and minus inputs. They're called rails. Generally about 12 or 15 volts. So these ones aren't always shown. Some usually just have a triangle with the 2 leads coming to the left and the 1 lead going out the right. But these guys have to be there again for this thing to work. So this is a typical sort of circuit that's on an op amp. So this is LM741 op amp. It's a whole bunch of transistors, resistors. So this is the whole thing that's on that little rectangular chip. You have an output over here, VS coming in and out, non-inverting input, inverting input. And so that's kind of everything that's involved. Here's another one. This guy has some diodes, resistors, transistors, and a capacitor as well. Again, these things are roughly very small, 1 square millimeter kind of chip, has all this stuff on it. So this is kind of what it looks like, just to give you an idea. So again, it has 8 leads. All these leads correspond to something. There's usually a notch up here so you know which one's on the top, and then you can kind of figure out which lead is which. So that's kind of what we're looking at. And again, this is roughly very small. It's, tiny little thing that has all that stuff, all those components on it. So all that stuff in that tiny little piece. So luckily, we don't have to worry about all that big disgusting circuit that I just showed you. Op amps generally work using some fairly simple rules. So they're operated to design to work according to this equation. So my output voltage is some open loop gain factor, A0, times V plus minus V minus. So essentially the difference between the input and output, difference between the positive and negative inputs is your V plus and V minus. So whatever that voltage difference is, times this gain factor gives you the voltage coming out. And so if you just connect it the way we have it here, this is called open loop. So V in has some ground. So difference between those two is just V in and V out is this open loop gain. Open loop gain is generally in the neighborhood of 10,000 to a million. So pretty significant voltage amplification there. If you connect it the opposite direction, so instead of having V in go to the positive input, have V in go to the negative input, and then ground be positive. Again, that's the inverting input, so it just makes it the opposite. So negative A0 is my gain in that case, just negative just indicating that it's inverted. And so open loop operation, like we just saw, there's 2 setups, inverting and non-inverting. The problem with open loop is that the output voltage almost immediately does something that we call hit the rails. So I have some voltage source coming in powering this thing. My voltage out can really never be higher than that because I can't just make up energy. So voltage out basically has to be less than the amount of voltage powering this thing. So if I put my input voltage in and start increasing it very, very slowly, well, if I have a gain of 1,000,000, even if I increase it by 1 microvolt, that's going to go up by 1 entire volt. And so increasing this thing only a few microvolts, I've already hit my output voltage of 15 volts coming in. So this is called hitting the rails. So very, very small changes in my input voltage make this thing jump to either the positive voltage source coming in or the negative voltage source going out, because again, this amplification is huge. And so it's very hard to stay within the tiny voltage domain that keeps you between positive VS and negative VS. So the takeaway from this is that open loop operation is not used very often because it's really hard to, again, have small enough voltage changes where you don't, hit the rails, like I said. So closed loop feedback, there's a couple types. So generally what it consists of is adding a line between V out back to the inputs. So there's this is called negative feedback. And so again, there's two types of that. There's the non-inverting input, which is called positive feedback. If you go to the inverting input, it's called negative feedback. So I have my feedback coming from V out, going back to the negative input on the op amp. If V in is going to the positive non-inverting input, and this is voltage feedback, if my V in is going to the inverting input as well, this is called operational feedback. In any event, if you use negative feedback, it causes the op amp to try to make the input potential difference 0. And so that's one of our main rules when analyzing op amps. So kind of summary of some things we've seen already. These are going to be our formal rules now. So first rule, ideal op amp, open loop voltage gain can be thought of as infinite. For an ideal op amp, real life, we're looking at 10 to the 4th to 10 to the 6th, but still very high, almost too high to be useful. The input impedance is very large, so something of the order of mega ohms. And the output impedance is very small, so 10 to 1,000 ohms. Rule 3 is another important one. The input terminals of an op amp draw practically no current in most cases. So what that means is, we'll see this again in examples, but if I'm coming in here, I'm expecting all the current to go up around this way because the current into this plus and minus terminal should be fairly small. So if there's another option for the current, it'll go that other way. So that's rule 3. And then if I have negative feedback, I have a 4th rule. The op amp is going to respond by feeding back as much current as voltage necessary to keep the input voltage difference equal to 0. So that's the plus and minus. It wants those two things to be equal to 0. So again, if I hook this up like this, it's going to try to make whatever comes back in this feedback network, there's going to be enough voltage to basically equate these two guys. So those are 4 rules we'll be using. We'll be using rule 4 and rule 3 a lot this week and next week. So again, here's a physical one I showed you before. Very compact form, tiny chip, millimeter size. This makes it a lot easier to connect to breadboard. So you have that channel down the middle of your breadboard. This is actually made to sit across that channel so that none of the leads are actually in contact with each other. So you can just set it up right down the middle, and then you have basically your 8 rows all doing whatever they're supposed to be doing: input voltages, source voltages, output voltage. So this is called the dual inline package. So 2 lines of 4 essentially. So a few other ways you can have op amps set up, but this is the ones we'll be using. So again here, usually you have a little notch, and that shows you which way to orient this. And then in terms of the pins, pin 1 doesn't really do much. Pin 2 is for my inverting input. Pin 3 is for the non-inverting input. Pin 4 is for the negative power supply. Pin 8 doesn't do much. Pin 7 is for the positive power supply. And then pin 6 is where my voltage comes out. Then 5 doesn't do much. Again, you can use them to do other things, number 1, 5, and 8, but a lot of times you don't. Again, this is just the common arrangement. You might want to check your data sheets just to make sure the one you have is the same. So again, these guys always need external power, so I'm always going to need some voltage source on one side, negative voltage source on the other. So make sure you actually hook up those connections as well, otherwise it's not going to work. And don't swap the polarities, so make sure your positive voltage is joined to the positive side and your negative voltage is joined to the negative side. Otherwise bad things might happen. If you want, you can put a diode in there to protect that from reverse polarity. So the diode's going to stop any negative voltage coming in one direction. Other methods to provide plus and minus voltage if you only have a positive voltage. So if you have batteries or 2 batteries or just 1 battery, you can get so positive 9 volts and negative 9 volts out of that, or positive 6 volts and negative 6 volts out of that guy. So last thing to do today is go over a few different op-amp circuit variations. So there's a few different ways we can hook this up that are very common. So we'll see a few today and then a few at the beginning of next week. And so the first one is called a unity gain amplifier or buffer. It's used to isolate the input voltage from the load. Like its name implies, unity gain, its gain is equal to 1. So if you want to kind of analyze what's going on here, the way to analyze this is to start off by using rule of 4. So we have negative feedback loop. I have a connection between V out and my negative terminal, usually with a resistor. And so because I have negative feedback, the 2 voltages, V plus and V minus, are going to want to be forced to be 0. So voltage difference between those 2 is 0. That means V plus is V in, because that's just what I have hooked up to V plus. So V plus has to be V in, because that's what's hooked up to it. And then the voltage difference being 0 means that V minus is the same thing, but V minus is hooked up to V out, as we can see, especially in this one up here. So my voltage at V minus is exactly V out. And so because of rule of 4, V plus is V in, V minus is V out, V in equals V out, or a gain of 1. So no amplification for that one. An inverting amplifier. So inverting means I've connected my negative feedback loop into the negative terminal, and V in is in the negative terminal as well. So for this guy, I have some current, we call it I1, coming across resistor 1 from V in into this joint, positive into the ground. And then on the V out, I have this negative feedback loop coming up. So I2 is going through some resistor R2 and hooked back up into the negative input terminal, V minus. Voltage gain in this case, V out over V in is minus R2 over R1. The way we can derive that, again, we start with rule 4. So rule 4 says that with this negative feedback loop, V plus and V minus, the voltages right here have to be the same. Since the positive sign is rounded, so I know that V plus is 0, that means that V minus has to be 0 as well, just by rule 4. Now that I know that, I can look at I1. So I1, if I look at this, is V in minus V minus over this R1. So voltage across R1 is V in minus V minus. V minus is 0, so I1 is just V in over R1. Similarly, I can do the same or similar thing for R2. So the voltage across R2 is V minus minus V out along that loop, but then V minus is 0, so it's just V out over R2. Rule 3 says that no current comes into my op amp, so because of that, the current I2 and the current I1 essentially have to be the same but opposite. So the way it's drawn here, I2 comes in, I1 comes in. So Kirchhoff current rule, I1 plus I2 equals 0. So I1 equals negative I2 or vice versa. And so I know that I2 is V out over R2. I1 is V in over R1. Solve that for V out over V in. And that's how we get negative R2 over R1 for the gain in this case. A non-inverting amplifier. So in this case, I have V in coming into the positive terminal. So that's going to give me a non-inverting amplifier. I still have negative feedback, so I still have a feedback loop coming from V out into the negative terminal. Generally here, resistors used are in the 1 to 100 kilo ohm range. And then I have it grounded up here, so kind of a voltage divider circuit on that side. Generally, in this case, you want the current in the feedback to be much larger than the V minus current. The gain in this case, V out over V in, is just kind of a voltage divider, R1 plus R2 divided by R1. That's going to be the gain for this guy. So if I'm using this 10 kilo ohm resistor and 1 kilo ohm resistor, that would give me a gain of 11 for this guy. So 10 plus 1 over 1 gives me a gain of 11. The way to derive that, again, as usual, rule 4 with negative feedback says that V plus and V minus have to be the same thing. V plus I can see is V in, so that means that V minus is also V in. And then using the property of voltage dividers, V minus is R1 over R2, R1 over R1 plus R2 times V out. So again, just solve that for V in over V out, gives you the equation we're looking for. And the last one we're going to see today is called a summing amplifier. So I can connect more than one output to my negative terminal. So I have V1 coming in over R1 with some current I1, V2 coming in over R2 with some current I2, negative feedback loop going through R3 and I3. So in this case, my amplification, V out, is minus R3 over R1 times V1, minus R3 over R2 times V2. And again, if I have more than this coming in, I can have as many as I want. Just kind of similar pattern for all of them, and that's going to give me essentially my gain. So also many other variations, which we'll see next class. There's also some variations where you can combine them. So I can have an inverting amplifier and a summing amplifier. So inverting amplifier over here, summing amplifier over here with 3 different inputs. So you connect these up in series or parallel and do all sorts of fun stuff with them. So again, we'll see a few more simple variations next class or next week, and then go on from there.